Hello and Assalamu alaikum everyone. Hope you all are studying hard and preparing well for your chemistry exam tomorrow. Today, for your last minute revision, we will be going through Chemistry's Unit 5 FAQ sheet. So without wasting any more time, because your exam is literally about to break the door anytime, let's get started. So in the first few pages, there are notes that you can go through to revise. So let's get started with the questions. Which pair of equations shows the most likely mechanism for vanadium 5 oxide acting as a catalyst in the contact process? So we know what the contact process is. It's basically a method for producing sulfuric acid, which is H2SO4. And one of its key steps is the oxidation of sulfur dioxide to sulfur trioxide. So I wrote the equation here, which is SO2 plus oxygen gives us sulfur trioxide. And this reaction, it's exothermic, but slow at normal temperature. So a catalyst is used to speed it up. In the vanadium 5 oxide, the V2O5, it's the catalyst employed in this process. Okay, so V2O5 is the catalyst. And we know what the role of a catalyst is. A catalyst speeds up a reaction without being consumed. It does this by providing an alternative reaction pathway with a lower activation energy. So in this context of the contact process, the V2O5, the vanadium oxide, it will facilitate the oxidation of sulfur dioxide to sulfur trioxide by undergoing reversible changes in its oxidation state. So let's look at the options. In option A, the V2O5 in the first equation, it reacts with oxygen and it forms V2O6. Here, the vanadium oxidation state, it increases from +5 here to +6. Okay, and then vanadium, the V2O6 here, it will react with SO2 and it gives back the V2O5 and gives us sulfur trioxide. This seems plausible, but if we check the oxidation state more carefully, we will see the vanadium in V2O5 is in +5 state, and if it forms V2O6, it basically has an oxygen added, and it makes it vanadium +6. Then it's reduced back to +5 here. But this it's not the most likely mechanism because typically vanadium cycles between the +4 and the +5 oxidation states in catalysis, not +5 and +6. And the second option, the first equation, the V2O5 plus SO2 produces V2O plus half O2 plus SO3. Here, the vanadium goes from +5 to +1. Okay, in V2O, which is a huge reduction. So this seems unlikely because such a large change in the oxidation state, it's not typical for the catalytic process. So let's go to the option C. So here in the first equation, the V2O5 will react with O2 and it forms VO3. So here the vanadium's oxidation state in V2O5 is again +5 and in VO3 it's still +5. So this does not show a change in the oxidation state, but we know it's necessary for redox catalysis. So this is also not the correct answer. And in the last option D, the V2O5 with the oxidation state of +5, it will react with SO2 and it forms V2O4 and SO3, sulfur trioxide. So here, the vanadium, it's reduced from +5 to +4. Okay? And the sulfur dioxide is oxidized to sulfur trioxide. And in the second equation here, the V2O4 is again oxidized back to V2O5 by oxygen, and the oxidation state goes back from +4 to +5. So basically option D is the correct answer. Moving on to the next question. So the formation of carbon dioxide from the reaction between manganate 7 ions and ethanediene ions is autocatalyzed by manganese 2 ions. The equation for this reaction is shown. So we have the equation here. And which graph for the complete reaction shows the autocatalysis of this reaction by the manganese 2 ions. So we have 4 graphs given. So this question basically describes a chemical reaction where the manganese 7 ions, the MnO4, will react with the ethanediene ions, which is C2O42 minus, in the presence of hydrogen ions, and it will produce carbon dioxide, manganese 2 ions, and water. So the key point here is that the reaction, it's autocatalyzed by manganese 2 ions, and we know autocatalysis means that one of the products of the reaction, and in this case it's Mn2+, will act as a catalyst for the reaction itself. Okay, and this implies that the reaction proceeds and the Mn2+ it's reduced, and the reaction rate will increase because the catalyst, which is Mn2+ concentration, its concentration increases. And we have to identify which graph correctly represents the volume of carbon dioxide produced over time for this autocatalyzed reaction. So for an autocatalyzed reaction, the rate of reaction and thus the rate of product formation will change over time due to the increasing concentration of the autocatalyst. So initially, it will have a slow phase. So at the start, there is little to no Mn2+ present, which is the autocatalyst. So the reaction will proceed very slowly. So the volume of carbon dioxide produced will increase gradually. And as Mn2+ it's produced, it catalyzes the reaction and causing the rate to increase. And the volume of carbon dioxide produced, it will also start to rise more steeply. And eventually, the reactants, which is O4 minus and C2O4 minus, 2 minus, it will be used up. So the reaction rate will slow down again and the volume of carbon dioxide will level off. So the graph that shows all this is option D. Okay, so there's a slow initial increase in carbon dioxide volume and there's a period where the rate increases and the curve becomes steeper. And finally, there's a leveling off as the reaction is completed. Okay, so this is the answer for this question. So moving on to the next question. Acidified potassium dichromate 6 is an oxidizing agent. The acid commonly used is sulfuric acid. Explain, using reference to the electrode potentials shown, why concentrated hydrochloric acid should not be used to acidify potassium dichromate 6. And here we are given the E0 values. So the question basically asks us why the concentrated hydrochloric acid should not be used to acidify the potassium dichromate 6, even though sulfuric acid is commonly used for this process. So in the answer, we have to refer to the standard electrode potentials provided in the table to explain the underlying redox chemistry. So we know the oxidizing agent, which is acidified potassium dichromate 6. It's a strong oxidizing agent, and in acidic solution, the Cr2O72 minus will oxidize the other species while itself being reduced to Cr3 plus. So the half equation will be this: Cr2O72 minus plus 14H plus 6 electrons will give us 2Cr3 plus 7H2O. And we are given the value. And the role of the acid is basically that the acid provides H plus ions, which are required for the dichromate reduction half reaction. In sulfuric acid, it's typically used because it is non-oxidizing and it does not interfere with the redox process. And the hydrochloric acid, it will contain the Cl minus, and that can be oxidized to the toxic chlorine gas by strong oxidizing agents like Cr2O72 minus. So the equation for the Cl minus oxidation would be the opposite basically. So the two Cl minus would form Cl2 and 2 electrons, and the E0 value will be opposite. So it's minus 1.36 volts because it's the reverse of the given Cl2 reduction potential, and to determine whether the Cr2O7 minus, it can oxidize the Cl minus to chlorine. We have to calculate the standard cell potential, which we know as the E naught cell value. And we know we calculate the E naught cell value, by, here we have the E naught oxidizing agent minus the E naught reducing agent. Okay, so here the oxidizing agent, which is this Cr2O7 2 minus with the value of plus 1.33 volts, and the reducing agent, which is Cl minus with a value of plus 1.36 volts. And if you reverse it for the oxidation, it will be minus 1.36 volts. So if you put it into this formula, here it will be equal to the oxidation, which is plus 1.33 volt, minus the reduction, which is plus 1.36 volts, and we get minus 0.03 volts. Okay, and this is a negative E naught cell value, and that suggests that the reaction is not thermodynamically feasible under standard conditions. However, the value is very close to 0, and it means that the reaction is basically on the borderline. And why the concentrated HCl will change the outcome? It's because of the Le-Chatelier's principle. We know when we use concentrated HCl, it will increase the concentration of H plus and Cl minus, and that will shift the dichromate half reaction to the right-hand side towards the more Cr3 plus and H2O will be formed, and this will increase the actual electric potentials, and it will go beyond plus 1.33 volts. So it will make the E cell value positive, and the reaction will become feasible. Okay, and the toxic chlorine gas, so the oxidation of Cl minus to chlorine becomes significant, and that will release the hazardous chlorine gas, and that's why the HCl should not be used, because it introduces a side reaction that is both dangerous and it interferes with the intended redox process. Okay, so the answer should be this one here. So under the standard conditions, the reaction, it's not feasible because the E cell value is negative, which is minus 0.03 volts, and the concentrated HCl, it will alter the conditions, the non-standard one, making the reaction feasible by increasing the E cell value, and the production of the toxic chlorine is the practical reason to avoid HCl. Okay, so moving on to the next question. The cell diagram for an electrochemical cell is shown. So we have an electrochemical cell, and the cell diagram is shown. So the question is, write the reduction half reaction for this electrochemical cell. State symbols are not required. Okay, so basically for the left half cell, we know it anode, which is anode basically. So oxidation will occur there, and the electron is the solid silver. Yeah, this solid silver is the electron. The electrolyte is the silver ions. And the half reaction will basically be Ag solid to Ag aqueous plus electron, of course. And on the right half cell, which is the cathode, the reduction will occur. So the electrode is the platinum, and it's an inert electron, so it does not participate in the reaction. The electrolyte, it's a mixture of vanadium species, so VO2 plus aqueous, and it has the oxidation state of plus 4, and the VO2 plus which has an oxidation state of +5, and H plus, and the water, which is used as a solvent or a product. So here, if you're balancing the equation, so the right half cell, it's where the reduction occurs. So we need to write the balanced half reaction showing the conversion of the higher oxidation state, which is VO2 plus, to the lower one, which is basically from this one to this one by gaining electrons. So, and for the species involved, we know VO2 plus, it's reduced to this one, it's reduced to this. And the H plus ions, they're present in the acidic medium. And the electrons, they're gained. And water is formed as the product. So if you write the equation, is this. So we have in the left-hand side the VO2 plus with a +1 charge and 2 hydrogen ions and 1 electron, giving us this VO2 plus and water. So here on the left-hand side, we have a charge, like the total charge. Here we have +1, +1, -1. So we have a total charge of +2. And on the right-hand side, we have this VO2 plus and water. So if you look at the charge, it has a total charge of +2. And there is one vanadium on the left-hand side, one vanadium on the right-hand side. There's 2 oxygen on the left-hand side, 2 oxygen on the right-hand side, 2 hydrogen on the left-hand side, and 2 hydrogen on the right-hand side. So basically, how did we come up to this? First, we will write this part. So this plus electron will give us this, right? So VO2 plus electron will give us VO2 plus. So here we have the vanadium balanced, but the oxygen, it's not balanced. We need one more oxygen here. So whenever we need oxygen, we have to add water to balance the oxygen. So we will add one water molecule here. Now we have both the sides have 2 oxygen and 2 oxygen here. But here's another problem that arises, that there's 2H, but here there's no hydrogen. So in order to balance it, we will again add hydrogen here. So H plus, which is 2H plus. So now if we write this, you see, all of it is balanced and we came up to this equation. Okay, it's the same one. Okay, so moving on to the next question. This question is about color transition metal complex ions. A, the Fe H2O6 2 plus complex ion, it's green, and the Fe H2O6 3 plus complex ion, it's yellow. Explain why the Fe H2O6 2 plus complex ion is colored. So basically, we have to explain why the complex ion, the hexaaqua iron 2, it's colored. So FeH2O H2O6 2 plus, it appears green. And the oxidized form, which is the FeH2O6 3 plus, it is yellow. And we know why the transition metal complexes are colored. So the transition metal complexes, they're colored due to the d-d electron transitions. So in a free Fe2 plus ion, all the 5d orbitals, they have the same energy. But when the H2O ligand, it binds to the Fe2 plus, they will create an octahedral field. and that splits the d orbitals into two energy levels. The lower energy set, which has the dxy, dxz, and dyz, and the higher energy set, which has the dz square and the dx square y square. So the energy gap between the two sets, it's called the ligand field splitting energy. And when white light, it hits the complex, some wavelengths to absorb to promote an electron from the lower energy level to the higher energy level, and the energy that is absorbed corresponding to a specific wavelength of light, it's complementary to the observed color. And the non-absorbed wavelength, they pass through and they are seen as the complex's color. So for FeH2O6 2+, the absorbed light, it is in the red region, and that's why the transmitted light, it will appear green, which is the complementary color. Okay, so the answer is the FeH2O6 2+ ion. It's colored because the water ligands, they cause splitting of the iron 2 ions, d orbitals into two energy levels, and when the light shines on the complex, some is absorbed to excite the d electrons from the lower energy level to the higher energy level, and the transmitted light, which is not absorbed, it gives the ion its green color. Okay, so this is the answer. So moving on to the next question. Explain why the two iron complex ions are different colors. So basically, it's because of three things: the different oxidation states of iron. So one is Fe2+, the other is Fe3+. Secondly, the changes in the d orbital splitting energy caused by the difference in charge. And thirdly, the different wavelengths of light absorbed, leading to different transmitted observed colors. Okay, so the FeH2O6 2+, it contains Fe2+ ions, which has a D6 configuration. So if I go back here, this one, it has Fe2+ ions and it has a D6 configuration. This one contains Fe3+ ions and it has a D5 configuration. And since Fe3+, it has a higher positive charge than Fe2+, it will attract the lone pairs of the water ligands more strongly, and that will increase the ligand field splitting. And the larger ligand field splitting in Fe3+, it will mean that it basically means the higher energy light, and higher energy light will have shorter wavelength, like the blue or violet. It will be absorbed for the DD transition. And the smaller ligand field splitting in Fe2+, it basically means lower energy light, and lower energy light has longer wavelength, which could be example red, and that is absorbed. So the Fe2+, which is the green complex, it absorbs the red light of lower energy, and that's why it will transmit the green color, which is complementary color of red. And for the Fe3+, it will absorb the blue or violet light, which has higher energy, and it will transmit yellow color, which is complementary color of blue. So the answer for this question is the two complexes, they have different colors because the iron ions are in different oxidation state. One is Fe2+, the other is Fe3+. The Fe3+ ions, the Fe3+ ion, it has a higher charge, causing stronger d orbital splitting compared to Fe2+, and as a result, the Fe3+ complex, it absorbs higher energy light, appearing yellow, while the Fe2+ complex absorbs low energy light, which is red light, appearing green. So this is the answer. Moving on to the next question. The complex ion formed from cobalt-3 ions and ethane-1,2 diamine is yellow-orange color. The equation for the formation of this complex ion is shown. So we have the equation here. Give a reason by referring to the equation why the formation of the diamine complex from the aqueous complex ion is thermodynamically favored. So we have the equation, and we see that in the reactant there is one complex ion here, and there is 3 ethane 1,2-diamine molecules. So total here we have 1 plus 3 particles. So total we have 4 particles on the left hand side or on the reactant side. And in the product side, we have 1 new complex, which is this one, in 6 water molecules. So total we have 1 plus 6. So total we have 7 particles. So from here, we see the number of particles. It increases from 4 to 7, leading to a more disordered system. So higher entropy. So entropy is more than 0. And even if the enthalpy change, the del H, it's slightly positive, which is endothermic. The plus T del S system, the plus T del S term, it can dominate. So it will make the del G negative, making it spontaneous. So more molecules equals to more ways to distribute the energy. So the del S is more positive or more than 0. And that's why the del G, it's less than 0. So the reaction is favored. Okay. So the answer should be the reaction is thermodynamically favored because it produces more molecules, which is 7, than it consumes, which was 4. And this increases the system's entropy. So del S is more than 0. And this entropy-driven process can make the del G negative, even if del H is slightly unfavorable. So here's the answer. Moving on to the next question. Explain by reference to the structure of ethane 1,2-diamine why it is a bidentate ligand. So we know a bidentate ligand, it can form 2 coordinative covalent bonds with a central metal ion because it has 2 donor atoms positioned appropriately to bind simultaneously. So here in the ethane 1,2-diamine structure, if you look at this, so each NH2 group, it has nitrogen atom with lone pair of electrons. There's NH2 and there's an H2. So as I was saying about the bidentate ethane 1,2-diamine. So here we have 2 NH2 NH2 group, which is here 1 and 2, and they have a nitrogen atom with lone pair of electrons. So this lone pair of electrons, they can donate electrons to the metal ion, and they can form the dative bonds. And the 2 carbon chain, the CH2 here, this keeps the nitrogen atoms close enough to bind to the same metal ion, but far enough to avoid steric clashes. So the 109-degree bond angles, which is the tetrahedral at N, it allows the ligand to wrap around the metal ion, and it forms a stable 5-member chelate ring. So the CO and CCN. So the answer should be that the ethane 1,2-diamine, it has 2 nitrogen atoms, each with a lone pair, and the CH2 spacer allows both nitrogens to coordinate to the same metal ion simultaneously, making it bidentate. So here is the answer. Moving on to the next question. Explain how the H and H bond angles would be expected to change in ethane 1,2-diamine when the complex ion is formed. So the H and H bond angles in ethane 1,2-diamine, it will change when it binds to a metal ion because of the lone pair to bond pair conversion and the hybridization change from the sp3 with lone pair to sp3 with bond pair. Okay, so the nitrogen in NH2, it has 3 bond pairs. So 2 NH bonds and 1 NC bonds. Yes, so 2 NH bonds and 1 NC bonds, nitrogen carbon bond, and 1 lone pair, so that's the non-bonding electron, and it's sp3 hybridized, and the electron geometry is tetrahedral and the molecular geometry is trigonal pyramidal. So the lone pair, it will repel the bond pair. And the H and H bond angle, it's 107, which is slightly less than 109.5 degree because of the lone pair repulsion. But after the complex is formed, the lone pair and the nitrogen, it will form a dative bond, the coordinate bond with the metal ion. And now the nitrogen will have 4 bond pairs. So 2 NH bonds and the 1 nitrogen carbon bond and plus 1 nitrogen and metal bond. And now there will be no lone pair because it's now part of the metal ligand bond. The electron geometry, it will remain tetrahedral because of sp3, but the molecular geometry, it becomes closer to ideal tetrahedral, which is 109.5 degree. And the H and H bond angle, it will increase to 109 because there's less distortion since the lone pair repulsion, it's gone. Okay, so the answer should be in 3-ethane 1,2-diamine, the hydrogen-nitrogen-hydrogen angle, it's 107 degrees, trigonal pyramidal, due to lone pair repulsion. And when it binds to a metal ion, the lone pair, it becomes a bond pair, reducing repulsion and increasing the angle to 109.5 degree, making it tetrahedral. So this is the answer. Moving on to the next question. Raspberry ketone can be synthesized in the laboratory from phenol using a Friedel-Crafts reaction. The overall reaction is shown. Draw the mechanism for this reaction using appropriate curly arrows. Include equations showing the formation of the electrophile and the regeneration of the catalyst at the end of the reaction. Okay, so basically here, we know. So firstly, let's talk about the formation of the electrophile. So the acyl fluoride, it will react with the AlCl3, the Lewis acid catalyst, and the acyl fluoride CO, the oxygen will donate a lone pair to AlCl3 and it will break the C-Cl bond. And this will basically form a positively charged ion, which forms the electrophile. And that electrophile will attack on the phenol, which is the aromatic ring. So the acyl group, it will attack the electron-rich phenol ring in the ortho or para to OH due to its activating effect. And we have to draw an arrow from the pi electron of the benzene ring to the carbon C plus of the ion. And of course, the deprotonation and the aromaticity restoration. So the sigma complex, which is the ion, it will lose a proton, H plus, to restore the aromaticity. So the AlCl4 minus, it acts as a base. It will remove the H plus and it will regenerate the AlCl3. So the catalyst regeneration will be shown by an equation, which is H plus AlCl4 minus, giving us AlCl3 and HCl. So if you look at the answer, it should make everything clear. Yes, here. So we have the electrophile formation at first, and then the curly arrows to show the attack on the phenol and the deprotonation by AlCl4 minus. And finally, the structure of raspberry ketone, methyl para hydroxyphenyl ketone. And lastly, it shows the catalyst regeneration. This one, the catalyst regeneration. So moving on to the next question. Give a reason why the yield of raspberry ketone by this method is not high. So basically, it asks us why the fetal crops acylation of phenol to produce the raspberry ketone, it will not give us a high yield. So phenol, it has an activating OH group and it makes the benzene ring highly reactive. And the acyl electrophile, the RCO plus, it can attack the ortho in two positions or para one position to the OH group. So that's why it will give us a mixture of ortho and para substituted products, and that will reduce the yield of the desired para raspberry ketone. So the ortho position, which is next to the OH, it's sterically crowded because of the bulky acyl group, and that can lead to a slower reaction rate or side reactions that will further lower the yield. Or it could be over-acylation. So since phenol is highly reactive, there is a risk of multiple acylations. So it could be a di or tri-substituted product. So the answer is the yield, it's not high because the electrophilic substitution can occur at both ortho and para positions of the phenol ring, leading to a mixture of products. Steric hindrance at the ortho positions and potential over-acylation further reduce the selectivity for the desired para substituted raspberry ketone. So here is the answer. Moving on to the next question. Next question. Raspberry ketone can also be synthesized in the laboratory using a Grignard reagent via a multi-step process. The overall reaction is shown. Devise this multi-step synthesis, give the reagents and condition for each step in the synthesis, including the formation of the Grignard reagent and the structures of the intermediate. Okay, so basically here, first we have to do the oxidation of phenol to benzoquinone. So the reagents or the condition, it is limited K2Cr2O7, which is potassium dichromate, plus sulfuric acid for mild oxidation. And it has to be warm, not reflux, to avoid over-oxidation. So the reaction will be phenol to benzoquinone. And it is to convert the phenol into a more reactive carbonyl compound for Grignard addition. Next step will be the formation of the Grignard reagent, which is CH3MgBr. So the reagent in condition is methyl bromide, CH3Br, plus magnesium in dry ether and hydrous condition. And the reaction will be CH3Br plus Mg, giving us CH3MgBr, which is methyl magnesium bromide. And we have to avoid water because Grignard reagents, they react violently with water. And third step will be the Grignard addition to benzoquinone. So condition or reagents, it's CH3MgBr to react with 1,4-benzoquinone from our first step, and it will be followed by hydrolysis with dilute acid. And the reaction will be the nucleophilic addition of the CH3 minus to one carbonyl group, and it forms a tertiary alcohol intermediate. And the acid hydrolysis, it will protonate the alkoxide to yield 2-methyl-1,4-hydroquinone. And the fourth step is the oxidation to raspberry ketone. So the reagent and condition is we have to use excess acidified K2Cr2O7 or H2SO4 under reflux to do the strong oxidation, and it will oxidize the hydroquinone intermediate to raspberry quinone, which is 4,4-hydroxyphenyl 2-butanone. The OH group, it will be preserved, while the second ring carbon is fully oxidized to a ketone. So the answer here, everything that I just told It's here. Yep. So moving on to the next question. The second step of the industrial preparation of the raspberry ketone, it involves the reduction shown. Suggests why the choice of reducing agent is particularly important in this reaction. Okay, so the structure, it shows the C double bond C, like carbon-carbon double bond, alkene, adjacent to a ketone, which is the C double bond O group. Here, the C double bond O group and the carbon-carbon double bond. And why is the choice of reducing agent critical? Because the reagent must selectively reduce the carbon-carbon double bond without affecting the ketone group here. So the desired product, it retains the ketone, which is essential for raspberry ketone structure and fragrance. And if it's reduced, it will form the alcohol, which will ruin the product. So a strong reducing agent like the NaBH4 or LiAlH4, it can reduce both the carbon-carbon double bond and the ketone, the C double bond O. And the industrial hydrogenation, it will typically use mild H2 with selective catalyst. And the catalytic hydrogenation is chosen because it preferentially reduces the carbon-carbon double bond over carbon-oxygen under mild conditions. And the catalyst surface chemistry, it favors the alkene absorption. So basically the answer is the reducing agent, it must be selective to hydrogenate only the carbon-carbon double bond without reducing the ketone, the C double bond O. Catalytic hydrogen, example H2 or PD, it is used because it targets alkenes under mild conditions, preserving the ketone functionality for critical raspberry ketone. So here is the answer. Moving on to the next question. The alpha ionone and beta ionone molecules are structural isomers. So we have their structures given here. And compare and contrast the stereoisomerism of these two molecules. On the structures, circle any features of the molecules that give rise to stereoisomerism. Okay, so we see both can exhibit the EZ, the geometric isomerism, due to a double bond here and here. And only alpha ionone, it shows optical isomerism, which is the chirality. And the EZ isomerism, the geometric isomerism, it occurs due to restricted rotation around a double bond, which basically is a carbon-carbon double bond. And both the alpha ionone and the beta ionone, they have the carbon-carbon double bond in their cyclic structures. And it allows the EZ formation. And the optical isomerism, the chirality, it occurs when a molecule has four chiral it has a chiral center, basically a carbon with four different groups. And in this structure that we're given, we can see only the alpha ionone, it has a chiral center due to its specific substitution pattern. So the answer should be that both alpha ionone and beta ionone, they show EZ isomerism due to their carbon-carbon double bond. However, only alpha ionone, it exhibits optical isomerism because it has a chiral carbon, while beta ionone, it does not have it. Okay, so that is the answer. Moving on to the next question. What color is vanadium 3 in aqueous solution? So here, all the colors of the different states are given. So we see vanadium 3, which is this one, is green color. So the answer should be B. An oxide of vanadium is the catalyst in one step of the contact process for manufacture of sulfuric acid. Which reaction involves the vanadium oxide catalyst, and how does the oxidation number of vanadium change during the process? So from the first question, we saw how the contact process and the vanadium and everything works. So from there, if you remember, the oxidation number, it changes from +5 to +4 to +5. And the reaction is basically the sulfur dioxide to sulfur trioxide. Okay? So I'm not explaining it again. So moving on to the next question. A student prepared a sample of aspirin. The equation for the reaction is shown. So here we are given the equation. And aspirin was recrystallized using an ethanol water mixture as a solvent. The student determined its melting temperature using the apparatus shown. And the student sample melted over a range of 8 degrees starting at 125 degrees Celsius. The published melting temperature of pure aspirin is 135, and which is a suitable liquid to go in the beaker. So here this question basically assesses understanding of the melting point determination for our recrystallization aspirin sample. So aspirin, it was synthesized and the it was recrystallized, purified using ethanol water mixture, and the student measured its melting point using the capillary tube apparatus that is shown in this diagram. And the problem is the sample, it melted over a wide range, which is 8 degrees Celsius, and it started at 125 degrees, versus the pure aspirin, which is 135 degrees Celsius. So the melting point apparatus setup, it shows us the capillary tube. It contains the aspirin sample, and the tube is immersed in a heated liquid bath in the beaker to uniformly transfer the heat. And the liquid, it must withstand the high temperatures, which is above 135 degrees Celsius, the aspirin's melting temperature, and it should not react with the apparatus or sample. So for the first one, the deionized water, we know the boiling point is 100 degrees Celsius, which is too low because because it boils before the aspirin melts. Second option, ethanol, is we know the boiling temperature as 78 degrees Celsius, which is also low because it boils even earlier. For C, the hexane, we know the boiling temperature is 69 degrees Celsius, which is also low. And lastly, the mineral iron, which has a boiling point of more than 200 degrees. So that is ideal because it has a high boiling point and it's stable. So the answer should be D. And it is chemically inert, so it will not react with aspirin and the apparatus. So that's why the answer, the most appropriate answer is D. So moving on to the next question. So which is likely to be the main impurity in the sample of aspirin? So we have to consider how aspirin is synthesized and what byproducts or unreacted starting materials might remain in the final product. So we know aspirin, like if you talk about the background on aspirin synthesis, we know aspirin, it's also known as acetyl salicylic acid, and it's synthesized through the esterification of salicylic acid, which is 2-hydroxybenzoic acid, with acetic anhydride, which is ethanoic anhydride. So the reaction is typically catalyzed by a small amount of sulfuric acid or phosphoric acid. And the possible impurities in aspirin during the synthesis could be the unreacted starting materials. So the salicylic acid, which is the 2-hydroxybenzoic acid, if the reaction it isn't complete, some salicylic acid might remain, or the acetic anhydride. So any excess acetic anhydride could remain, but it's usually hydrolyzed by water during the workup, and the byproduct, which is acetic acid or ethanoic acid, this is a byproduct, and it is formed when the acetic anhydride, it will react with salicylic acid. And the other byproducts, so it could be other minor byproducts depending on the conditions, but they're less likely to be the main impurity. So if you look at the options, in option A, ethanoic acid, which is also the acetic acid, it's a byproduct of the reaction, but It's soluble in water, so it's often removed during purification by washing with water. And it won't crystallize with aspirin, so it's less likely to be the main impurity in the final crystalline product. Option B, ethanoic anhydride, which is the acetic anhydride. It's the starting material, and any excess, it's usually hydrolyzed by water during workup, and it's turned into acetic acid. And like acetic acid, it's not likely to crystallize with aspirin, so it's also unlikely to be the main impurity in the sample. Option C, ethanol. So here, ethanol, it isn't typically involved in the standard synthesis of aspirin, and even if it is involved, even if it's present, it's soluble in water, so it will not crystallize with aspirin, and it makes it unlikely to be the main impurity. So lastly, option D, 2-hydroxybenzoic acid, which we know as salicylic acid. It is the starting material, and it will react with the acetic anhydride. And if the reaction, if it isn't 100% complete, some of the salicylic acid will remain, and salicylic acid, it's less soluble in water than acetic acid or acetic anhydride. So it's more likely to co-crystallize with aspirin. So which is why the answer is D. Moving on to the next question. So this question is about cell reactions involving chromium. Use your data booklet when answering this question. A1, name the type of the forward reaction that is shown in the right-hand electrode systems in the data booklet. So we know the answer should be reduction, because in standard electrode potential notation, which is given in the data booklet, the right-hand electrode system, it represents the reduction half reaction. For example, for chromium, it could be Cr3 plus electron giving a Cr2 plus. So that's the reduction process where Cr3 plus, it gains an electron to form Cr2 plus. Second, name the series form when the right-hand electrode systems are placed in order, most negative first. So that is basically the electrochemical series. So when the standard electrode potentials, the reduction potentials, are arranged from most negative to most positive, the resulting list that we get, it's called the electrochemical series. And this series basically helps us to predict the relative oxidizing or reducing strength of species. Moving on to the next one. B, students set up the following apparatus to measure the standard electrode potential for a right-hand electrode system 8 in your data booklet. We have to identify X and Y. So the apparatus, it includes a hydrogen gas, which is the reference electrode, the standard hydrogen electrode, which we know as SHE, S-H-E, the platinum electrode, the platinum electrode, which is the inert conductor for the hydrogen electrode. And we have 1 mole per dm cube hydrochloric acid, which provides the H plus ions for the SHE. And of course, the salt bridge. The salt bridge, which contains aqueous KNO3 to maintain the ionic balance. And the right-hand electrode system 8, it likely involves a Cr3 plus and Cr2 plus ions. So for X, it should be platinum, because the hydrogen electrode, it requires an inert platinum electrode to facilitate the reaction. And for Y, it should be 1 mole per dm cube of Cr3 plus and 1 mole per dm cube of Cr2 plus, because to measure the standard electrode potentials for the Cr3 plus Cr2 plus system, the electrode system 8, the solution has to contain both the oxidized, which is the Cr3 plus, and the reduced, which is the Cr2 plus forms, at 1 mole per dm cube concentration. Okay. Moving on to the next question. Give 2 reasons why the initial reading on the voltmeter may differ from the stated value given in the data booklet. So this refers to a scenario where the student will measure the standard electric potential of a half cell, which is, let's say, Cr3 plus Cr2 plus, using a hydrogen electrode, She, and a voltmeter, but the observed voltage, it does not match the theoretical value from the data booklet. So the standard electric potential assumes ideal conditions. Okay, so it has to be 1 mole per dm cube concentration of ions, 298 Kelvin, which is also 25 degrees Celsius temperature, 1 atm pressure for gases like, let's say H2, and no side reactions or impurities. And if these conditions, they are not met, the voltmeter reading will differ. So the Cr3 plus, it's rapidly oxidized by the oxygen in the air because Cr2 plus is unstable and easily oxidized to Cr3 plus by the atmospheric oxygen, and that reduces the Cr2 plus concentration. So it will shift the equilibrium and alter the measured potential. And another reason could be the temperature, which might not be standard. We know the electric potentials, they're temperature dependent. So if the experiment is conducted at a higher or lower temperature, the voltmeter reading, it will deviate from the standard value. Okay. Moving on to the next question. The voltmeter, it's removed and the cell is allowed to run for 1 hour. Explain the changes that would occur in the right-hand half cell during this time. So basically a voltmeter, it's removed from an electrochemical cell. Here, this, it basically means that the circuit is closed and it's allowing the current to flow, and the cell is allowed to run for 1 hour. So it implies a spontaneous redox reaction occurring over time. And it asks about the changes in the right-hand half cell, which contains the Cr3 plus Cr2 plus system. So the concentration of Cr2 plus, it decreases as the E cell is positive. So the blue-green becomes greener. So let me explain this. So when we remove the voltmeter, basically the voltmeter, it measures the potential difference without allowing a significant current flow. So when it's removed, the cell will operate as a working electrochemical cell. So the electrons will flow from the anode oxidation to the cathode where reduction occurs, and the spontaneous redox reaction occurs if E cell is greater than 0. And the right-hand half cell, which we're assuming as the standard notation, is the reduction half reaction where the Cr3 plus, it gains an electron and it forms Cr2 plus, and the E naught value is minus 0.41 volts. And the left-hand half cell, it's the standard hydrogen electrode, which we know as She. So there, the 2H plus will gain 2 electrons and form H2, and the E naught is obviously 0 volt, and we know the cell potential, it's E cell equals to cathode minus anode. So if the E cell it's more than 0, the reaction will proceed. So the Cr3 plus Cr2 plus, it's more negative than She. So the She will act as the cathode. So it will be the reduction. So H plus will form H2, and the Cr2 plus will act as the anode where oxidation will occur. So the Cr2 plus will change into Cr3 plus an electron. So charges in the right-hand half cell, basically it will decrease in the Cr2 plus concentration, since Cr2 plus, it's being oxidized to Cr3 plus, the concentration decreases over time. And the product of oxidation, which is Cr3 plus, it will accumulate in the reaction. So the color change will occur. So Cr2 plus, it's typically blue because of the CrH2O6 2 plus. And the Cr3 plus, it's green or violet because of the CrH2O6 3 plus. So as Cr2 plus, it decreases and Cr3 plus, it increases, the color will shift from blue-green to a more green color. So that is the answer. Moving on to the next question. Explain by calculating E0 cell values why Fe2 plus is used to reduce Cr6 to Cr3, but zinc is used to reduce Cr6 to Cr2. Numbers chosen of the right-hand electrode systems from the data booklet. Okay, so it references the specific electrode system from the data booklet. So, which is 21, 28, 5, and 8, and requires the calculation of E cell values for the redox reaction and an explanation why the Fe2 plus, it stops at Cr3, while the zinc can go farther to Cr2. So we know the standard reduction potentials. The more positive E0, the stronger the oxidizing agent, and the more negative E0, the stronger the reducing agent. And it determines the cell potential. It determines if the redox reaction is spontaneous. So if the E cell value is more than 0, the reaction is spontaneous. And if we assume the following, like let's say system 21, where it's Cr2O72 minus plus 14H plus 6 electron, it gives us Cr3 plus and water. So the E0 value is plus 1.33 volt. So it's chromium 6 to chromium 3. And system 28 tells us Fe3 plus will gain 1 electron. It forms Fe2 plus, and the E0 value is plus 0.77 volts. System 5 tells us zinc 2 plus, and plus 2 electrons. It will give us zinc, and the E0 value is minus 0.76. And system 8 tells us Cr3 plus an electron. It gives us Cr2 plus, and the E0 value is minus 0.41 volts. So the reduction of Cr6 to Cr3 by Fe2 plus, the half reaction, and basically the oxidation in the anode, it's Fe2 plus to Fe3 plus and plus electrons. So the anode, it's 0.77, which is of course a reverse of system 28. And in the reduction in the cathode, the Cr2O72 minus plus 14H plus 6 electron, it gives us 2Cr3 plus 7H2O. So in the cathode, it's plus 1.33 volt, which is system 21. So the cell potential we know would be 1.33 minus 0.77. So it gives us plus 0.56. And here, the E cell, it's more than 0. So Fe2, it can reduce Cr6 to Cr3. And for the further reduction of Cr3 to Cr2 by Fe2, so the half reaction in the anode, the oxidation would be Fe2 to Fe3, and the E0 value for the anode is plus 0.77, and the reduction in the cathode would be Cr3 plus to Cr2 plus, and the E0 value for the cathode is minus 0.41 volt, which is system 8. So if we calculate the cell potential from there, the E cell value is minus 0.41 minus 0.77. So from here we get the E cell value as minus 1.18 volt. So we see the E cell value, it's less than 0. So Fe2 plus Fe2, it cannot reduce the Cr3 to Cr2. And in the next one, for the reduction of Cr6 to Cr3 by zinc, the half reactions in the anode, the oxidation basically, where oxidation occurs, would be zinc to zinc 2 plus, and the E0 anode value is plus 0.76 volt, which is the reverse of system 5. And the reduction in the cathode, it's the half equation, would be Cr2O72 minus plus 14H plus 6 electron. It gives us Cr3 plus water, and the E cathode value, E0 cathode, it's plus 1.33. And if you calculate the cell potential, it comes as 1.33 minus 0.76. So it's plus 2.09 volts. So we see that zinc, it can reduce the Cr6 to Cr3. And lastly, the further reduction of Cr3 to Cr2 by zinc, So the oxidation anode is zinc to zinc 2 plus, which is plus 0.76 volt. And in the cathode, it's Cr3 plus to Cr2 plus, and the value is minus 0.41 volt. So the cell potential comes as minus 0.41 minus 0.76, which we get as plus 0.35 volts. So this is more than 0, the E cell value. So zinc, it can reduce the Cr3 to Cr2. So if you look at the answer, yeah, it's everything that I just explained right now. So moving on to the next question. Oh, state the essential condition required for this reaction to occur. So we know the role of H plus ions in Cr6 reduction, the reduction of dichromate, which is Cr2O72 minus to Cr3 or Cr2, it requires hydrogen ions to balance the reaction, because we know the example of the half reaction was Cr2O72 minus plus 14H plus 6 electron will give us 2 Cr3 plus 7H2O. So without the acid, the H plus, the reaction cannot proceed because there are no protons to form the water or stabilize the reduced chromium species. And in the neutral or alkaline condition, the Cr3, it forms insoluble hydroxide, and the Cr6, it exists as dichromate, CrO42 minus, it will exist as chromate, the Cr6, instead of dichromate. And the acid, it maintains the chromium insoluble reactive forms. So the answer for this one is acidified solution. Moving on to the next question. The mass spectrum of 2,6-dichlorophenol is shown here, and explain the relative intensities of the peaks at MZ values of 162, 164, and 166. So here, the so we know the isotopes of chlorine, which is which are two stable isotopes of chlorine. So one is chlorine 35, which has a 75% natural abundance, and chlorine 37, which has a 25% natural abundance. So from 75 to 25, we get a 3:1 ratio for single chlorine molecule. So the molecular ion of 2,6-dichlorophenol. So the molecular formula is C6H4Cl2O, and the base mass, so the C6H4O, it contributes 108 atomic mass unit. So basically C6H4O, because 6 into 12. As I was saying, the C6H4O, it will contribute to 108 atomic mass unit, because 6 times 12 plus 4 times 1 plus 16 gives us 108. And if we add 2 chlorine atoms, so chlorine 35 basically, so Cl35. So that would give us 108 plus 35 plus 35, and it gives us the 162 atomic mass unit, which it is talking about in here, 162. And if we add if we add 1 chlorine 35 and 1 chlorine 37, let's do this. So we add chlorine 35 plus chlorine 37. So we would get 164. Okay, and if we add chlorine 37, 2 chlorine 37s basically, so we get it as 166. Okay, so the probability of 2 chlorine is 0.75 square because this was 75% abundance. So it gives us 9 parts. And for one probability of 1 chlorine and 1 chlorine 35 and 1 chlorine 37 is basically 2 times 0.75 times 0.25, which we get as 0.375, so which is 6 part. And the probability of 2 chlorine 37 is basically 0.25 square, which we get as 0.0625, which gives us 1 part. So that is how the 9:6:1 ratio comes for 162, 164, and 166. Okay, so the answer for this one is this. Moving on to the next question. Suggest why there is a corresponding set of peaks that ends at values of 163, 165, and 167. So the primary peaks, it was 162, 164, and 166. They're from the molecular ion of 2,6-dichlorophenol with different chlorine isotopes in the smaller peaks at +1 mass unit, which is 163, 165, and 167. It's because of the natural presence of carbon-13 in the molecule. So carbon, we know it has 2 stable isotopes, carbon-12 with a 98.9% abundance and carbon-13 with a 1.1% abundance. So in a molecule with 6 carbon atoms like 2,6-dichlorophenol, there is a measurable probability that that one carbon is carbon-13 instead of carbon-12. So the base peaks 162, 164, and 166, they all assume that all carbons are carbon-12. But if one carbon-12 is replaced by carbon-13, the mass will increase by 1 unit. So that's how we get 163, 165, and 167. And for a for a 6 carbon molecule, the probability of 1 carbon-13, it's basically 6 times 1.1%, which we get as 6.6% of the base peak intensity. So the +1 peaks, they're smaller, but follow the same 9:6:1 chlorine isotope ratio as parent peaks. So the answer is...
Are you still stuck in chapter 1? Well, your exams are racing closer. You have watched thousands of videos on YouTube, but your marks are not moving. It's not you, it's the method. Let's fix it. Welcome to Exam Essentials, where every second counts and every session hits. You have seen our question solving walkthroughs, right? Now it's time to go all in. We offer 2 signature courses for A level and O level students. The first one is the High Impact Crash Course, which is basically launched 5 to 6 months before every exam session. Whether it's May 26, October 26, or any future sessions, this course is your fast track to results. For the upcoming October 25 and the January 2026 sessions, our High Impact Crash Course will be starting from June 1. So book your seats as soon as possible. Now the second course that we always offer is the complete 1-year course designed for students preparing for May 26, October 26, January 2027 and beyond. To know more, check the description box or message us directly on WhatsApp or on our Facebook page Exam Essentials. Stop struggling, start scoring. You have seen us on YouTube. Now it's time the world sees you succeed. Your top grade is waiting. Let's go get it together.
Moving on to the next question. 2,6-dichlorophenol. It's used for communication between ticks, small parasites that can infect animals, including humans. The compound can be synthesized in the laboratory from phenol. 4-phenyl sulfonic acid is formed in reaction A. This is then fluorinated. Hydrolysis of intermediate compound B removes the sulfonic acid group. The reaction scheme is shown. So we are given the reaction scheme in A1. Says the sulfonation of phenol is similar to the sulfonation of benzene. Suggest the reagents required for reaction A. So reaction A is this one. So 2,6-dichlorophenol is the signaling compound used by ticks, and it's synthesized from phenol via 3-step process. So the reaction A, it's the sulfonation of phenol to 4-phenyl sulfonic acid, and then chlorination of 4-phenyl sulfonic acid to intermediate B, and hydrolysis of B to 2,6-dichlorophenol. So in the part A1, it asks for the reagents needed for reaction A, which is the sulfonation of phenol, and gives us a hint that it's similar to benzene sulfonation. So the sulfonation, it introduces a SO3H group to an aromatic ring here, which is phenol. And for benzene or phenol, the classic reagent, it's the fuming sulfuric acid, which is oleum. SO3 in concentrated sulfuric acid, and SO3, it acts as the electrophile attacking the electron-rich ring, and the OH group in phenol, it's activating and ortho or para-directing. So sulfonation of the para position, the fourth position, is favored to avoid the steric hindrance from the OH group. So here is the answer. So we know benzene sulfonation, it uses oleum, fuming H2SO4 or SO3 gas, and the phenol's OH group, it makes it more reactive. So the milder conditions like concentrated H2SO4 alone might work, but it's less efficient. And SO3 in fuming H2SO4, it's a strong electrophile, ensuring complete sulfonation, and directs the SO3H group to the fourth position, para to OH. Moving on to next question. Deduce the structure of intermediate compound B. So phenol to 4-phenyl sulfonic acid, and that from 4-phenyl sulfonic acid to intermediate B by chlorination with Cl2. So basically, we know 2 chlorine atoms. They are at positions 2 and 6, which is at ortho to OH, and that means the chlorination must have occurred adjacent to the OH group. In hydrolysis of intermediate B, it will remove the SO3 group, leaving the 2,6-dichlorophenol structure. Yeah. And thus intermediate B, it must have the same 2,6-dichloro substitution pattern and a SO3H group, since hydrolysis removes it. Okay, and the SO3H group, it's a meta-directing substituent. It deactivates the ring but directs the electrophiles to meta positions. But OH, it's ortho-para-directing and it strongly activates the ring. So there's a competition between OH and SO3H. So the chlorine will preferentially add ortho to OH at positions 2 and 6 because the OH, it dominates over the SO3H in the directing effect, stronger activator. And the steric hindrance from SO3H, it discourages substitution at position 4. So the structure of intermediate B, chlorination at position 2 and 6, ortho to OH, and SO3H remains at position 4, original sulfonation site. So the structure should be this. And the name is 2,6-dichloro 4-phenyl sulfonic acid. Moving on to the next question. Explain why the reaction of chlorine with phenol occurs under milder conditions than the reaction to chlorine with benzene. So basically we have to identify the key electronic effect, the oxygen's lone pair delocalization into the ring. So the electrophilic aromatic substitution, both benzene and phenol, they undergo electrophilic aromatic substitution with chlorine, but phenol, it reacts much faster and under milder conditions like room temperature and no catalyst. So benzene plus chlorine, it will give us chlorobenzene, and it will require FeCl3 catalyst and heat. And for phenol, it will react with chlorine, and it will give us 2,4,6 trichlorophenol, and it occurs instantly at room temperature, and it's often uncontrollable. So it's because the difference is because the OH group in the phenol, it activates the ring by two mechanisms. So one is a resonance mesomer effect. So the oxygen's lone pair, it delocalizes into the ring, the pi donation. So it increases the electron density at ortho-para position, and this stabilizes the intermediate, the carbocation, during the electrophilic aromatic substitution. And secondly, the inductive effect. So the electronegative oxygen, it will withdraw the sigma electrons. So this is overpowered by resonance donation in phenol. And benzene's low reactivity, the benzene has no activating group. So it's pi system, it's electron neutral. So chlorine, it requires a Lewis acid catalyst, which is FeCl3, to polarize the Cl-Cl bond and generate Cl plus, the electrophile. So the answer is that the lone pair of electrons in the oxygen atom of OH in phenol, it will overlap with the pi electrons on the ring, increasing its density. Moving on to the next question. An alternative synthesis of 2,6-dichlorophenol starts with compound C. Compound C is chlorinated and hydrolyzed, and then the CO2 group is removed, decarboxylation, to form 2,6-dichlorophenol. Other than phenol, name the functional group present in compound C. So we see in C, other functional group is this, the COOR basically. So that we know as the ester. So that's another functional group. Moving on to the next question. Identify 3 factors that organic chemists would take into account when considering alternative methods for an organic synthesis. So basically, the process, it involves chlorination of compound C, hydrolysis of, chlorination of compound C, then hydrolysis of the chlorinated intermediate, and then decarboxylation, which is removal of carbon dioxide to yield 2,6-dichlorophenol. So for this one, one of the options could be the number of steps in each reaction sequence. So we know the fewer steps that generally mean higher efficiency and lower cost, or it could be whether the side reactions occur. So unwanted side reactions, they basically reduce yield and complicate the purification. Another answer could be whether the purification is required after each step. So extra purification will increase the time, cost, material loss, and carbon dioxide emissions. So environmental impact is important in green chemistry. In availability or cost of reagents or catalysts, so expensive or rare reagents, they make the synthesis impractical. Then percentage yield of each step. So higher yield, it means less waste and better efficiency. Another answer could be toxicity of reagent, intermediates, or byproducts. So the hazardous chemicals, it poses safety and disposal issues. And lastly, atom economy of the product, which measures how efficiently atoms from reactants are used in the final product to minimize waste. So this is the answer. Moving on to the next question. The final step in the synthesis is shown. State the type of reaction, the reagents, and the conditions. So we see the type of reaction, it's hydrolysis. Because we are breaking a bond using water. The reagent is aqueous acid. It could be HCl or H2SO4. And the conditions is heat under reflux to ensure complete reaction and prevent loss of volatile substance. So hydrolysis, we know it's a common reaction where the water splits a molecule, basically converting an ester to a carboxylic acid and alcohol. And the aqueous acid, it provides the H plus ions needed to catalyze the reaction. And heating under reflux, it ensures the reaction it goes into completion while avoiding evaporation of solvents or reactants. Moving on to the next question. In liquid tap detergents, glycerol is added to polyethanol. So give the IUPAC name for this molecule. So we see there's 3 carbon atoms here. 1, 2, 3. So it has to be it has to start with pro. And there is 3 alcohol group. So triol. And it's in position 1, 2, 3. So it's 1, 2, 3 triol. So basically the name is propan 1, 2, 3 triol. Okay, moving on to the next question. Which successive ionization energies in kilojoule per mole are most likely to be those of a transition element? So, successive ionization energies, we know it increases as more electrons are removed from an atom because the remaining electrons, they experience a stronger nuclear attraction. So a big jump in the ionization energy occurs when an electron is removed from a lower energy level closer to the nucleus after all electrons from a high energy level has been removed. In the transition metals, we know they're in the D block of the periodic table, meaning their outermost electrons are in the D subshell. So their ionization energy pattern typically shows no large jumps in the first few ionization energies, since multiple d electrons can be removed with similar energy costs, and a big jump only after all 4s and 3d electrons are removed when core electrons are being ionized. So in option A, we see a big jump between the third and the fourth ionization energy, which suggests removal of 3 valence electrons before core electrons. So this matches group 3, but not a transition metal, since transition metals have more variable oxidation states. In option B, there is no big jump, which suggests multiple electrons are removed with similar energy, that is from the same shell, and this is typical of transition metals where several 4s and 3d electrons, they can be removed before a big jump occurs. And in option C, we see a big jump between the fourth and fifth ionization energy. So we know it's 4 valence electrons removed, so it's group 4. In option D, we see a big jump between the third and the fourth ionization energy, again, which suggests that group 3, not a transition metal. So the answer is B. Moving on to the next question. Which sequence shows the ions in order of increasing strength as a reducing agent? Refer to your data booklet. So the reducing agent strength, we know a strong reducing agent, it will readily donate electron and it is easily oxidized. The weaker the reducing agent, the less readily it loses electrons. And the more negative or the less positive the E naught values are, the stronger the reducing agent. So for Fe2 plus, we know the E naught value is 0 plus 0.77, which is the weakest reducing agent. For V2 plus, it's minus 0.26, and for Cr2 plus, it's minus 0.41 volt, which is the strongest reducing agents. So if we go to all the options, for option A, V2 plus, Fe2 plus, and Cr3 plus, so it's incorrect because V2 plus is stronger than Fe2 plus. In option B, it is also incorrect because Cr2 plus is the strongest, not the weakest. In option C, it's also incorrect because Fe2 plus, it's the weakest, not the strongest. And the last option, it is correct because Fe2 plus has the least negative or the most positive E naught value, so it's the weakest reducing agent. V2 plus is the intermediate, and Cr2 plus, it has the most negative E naught value, and that's why it's the strongest reducing agent. Moving on to the next question. Peptides are short chains of amino acids linked by peptide bonds. How many different types of amino acids have joined to form the octapeptide? So if we know peptide bond is basically the CONH bond. So if you look at the CONH bond in all the places, CONH, if we break it down, we will see the amino acids. So we get one amino acid here. We get another amino acid here. We get another amino acid here, 3. But if you look at it properly, this, and these 4 are literally the same amino acid, so we can consider them as one type of amino acid. So that is 1, 2, 3, and we have another one here, which is 4, and the last one, here, which is the 5th type of amino acids. So we get 5 different types of amino acids, so the answer is B, 5. Next question, which shows the structure of the amino acid lysine as a solid and in solution at high pH. So we know as a solid, it exists as a sweeter ion form, and in high pH, which is the basic solution. So in solid state, the amino acid, they exist as sweeter ions. So the carboxyl group, it will lose a proton and become COO minus. Here, COO minus. In the amino group, the NH2, it will gain a proton and it will become NH3 plus. And lysine, it has an additional NH2, which remains neutral here. And about the amino acid in high pH, which basically means the basic solution. At high pH, we know the solution is basic. So whenever it's basic, it has excess OH minus ions. So the NH3 group from the amino group, it will lose a proton and it becomes NH2. And the side chain, the NH3 group, if this present, it will lose a proton, it will become NH2. And the carboxyl group, it will remain as COO minus because it's already deprotonated. So if you look at this, only B is the correct answer, which matches with our explanation. Moving on to the next question. A dipeptide has molecular formula C7H12N2O3. The dipeptide. So as I was saying, a dipeptide, it has a molecular formula of C7H12N2O3. The dipeptide, it's hydrolyzed to form 2 amino acids. One of the amino acids produced does not have a chiral center, What is the structure of the other amino acid which does not have a chiral center? The question, it presents a dipeptide. So basically a molecule formed by two amino acids linked by a peptide bond with the molecular formula of C7H12N2O3. So when this dipeptide is hydrolyzed, basically broken down by water, it splits into two amino acids. So one of the amino acid, it has no chiral center. So the amino acid, the only amino acid without a chiral center is glycine, which is, okay, it's this one here. This NH2, CH2COOH, and the other amino acid, it must have a chiral center. So we have to determine the structure of the second amino acids with the one with a chiral center. So the dipeptide formula we are given. And when hydrolyzed, it breaks into two amino acids plus water. So we know glycine will be one of the product. And since glycine has no chiral center, it must be one of the hydrolysis products. And the total atoms in dipeptide, so we have this. C7H12N2O3, and if you subtract the glycine and account for hydrolysis, which adds water, so we will get the dipeptide. It equals to amino acid 1 plus amino acid 2 minus water. Because we know when forming a peptide bond, we release water and the hydrolysis reverses this. So if we make this as the subject, the amino acid 2, we get dipeptide plus water minus the amino acid 1, which was glycine basically. So if we do this, we get the answer as H9NO2, which is basically C5H7NO plus water. So the second amino acid, it must have the formula C5H9NO2, and it has to have a chiral center. So chiral center, again, it's a carbon with 4 different groups attached. So if you look at these options, only option C matches with the explanation, which is why option C is the answer. Moving on to the next question. Sodium thiosulfate can be used to determine the concentration of an iodine solution by titration using starch indicator. 5 grams of sodium thiosulfate was dissolved in deionized water, and the solution made up to 250 cm³ in a volumetric flask. The volumetric flask has an uncertainty of plus minus 0.25 cm³. What is the minimum uncertainty of the balance required to match the uncertainty of the volumetric flask? Assume two weighings are needed. So basically sodium thiosulfate solution, we have a mass of 5. Okay, so if we basically go to the uncertainty propagation, we know for the volumetric flask, the uncertainty will be the absolute uncertainty divided by volume, which is here 0.25 divided by 250, and that should be equals to 2 times because there are 2 weighings, divided by 5, which was, where is it? The mass, here, the 5 gram. Okay, so if we solve this, we get x as 0.0025, so the answer should be A. Moving on to the next question. The titration was carried out with sodium thiosulfate in the burette and starch was added just before the end point. What would be the color of the solution in the conical flask at the end point. So we know sodium thiosulfate, it is in the burette, which is the titrant. And starch indicator, it's added just before the end point to detect the remaining trace amounts of iodine. And the goal is to determine the color of the solution in the conical flask at the exact end point. So the titration is based on the reaction of here 2 Na2S2O3 plus I2, giving us 2NaI plus Na2S4O6. So the sodium thiosulfate, it reduces the iodine to iodide, I minus, while itself is oxidized to tetrathionate, the S4O62 minus. So the starch, it will form a deep blue-black complex with iodine, and it is added just before the endpoint to avoid premature binding, which can make the endpoint harder to observe. So before titration, the conical flask, it contains iodine, which is brown in solution. So during titration, as the thiosulfate is added, the iodine will be consumed and the brown color will fade. So near the end point, when most of the iodine is reacted, starch is added, and any remaining iodine, it will form a blue-black complex. And at the end point, the last trace of iodine is reduced, causing the blue-black color to disappear, and it will leave the solution colorless. So from here, we can easily assume the solution will be colorless. So which is why the answer is C, because at the end point, all iodine is reduced and the blue-black starch iodine complex, it vanishes, so it leaves the solution colorless. Moving on to the next question. In 1865, Friedel August Kekulé suggested a structure for benzene which consisted of alternating single and double carbon-carbon bonds. However, modern analytical techniques indicate a structure in which the electrons are delocalized. Explain how the results of X-ray diffraction experiments on benzene suggest a delocalized structure rather than the Kekulé structure. So the Kekulé structure in 1865, it proposed benzene as a hexagon with alternating single carbon, like single carbon-carbon bond and double carbon-carbon double bonds, and implies the unequal bond lengths because the double bonds, they're shorter than single bonds, and the modern delocalized structure in it, the electrons in benzene, they're delocalized, so they're spread evenly over all 6 carbon atoms, and all the carbon-carbon bonds, they're identical in length because basically they're the intermediate between single and double bonds. And the X-ray diffraction, it measures the bond length and molecular geometry. So if Kekulé's structure was correct, the X-rays would show smaller or shorter carbon-carbon double bond, which would have been 1.34 angstrom, and longer carbon single bond, which is approximately 1.54 angstrom. But the actual experimental results, it shows that all carbon-carbon single bonds in benzene are the same length, which is 1.39 angstrom. So this will match the delocalized model where the electron density is evenly distributed. So the X-ray diffraction, it shows that all carbon-carbon bonds in benzene, they are the same length. And this suggests that electrons, they're delocalized or evenly distributed, giving bonds of intermediate length. So this is the answer. Moving on to the next question. The compound 1,2-dichlorobenzene exists as only one structure. Explain how this supports a delocalized structure of benzene rather than the Kekulé structure. Okay, so in the Kekulé structure, if benzene had fixed single and double bonds, thus substituting 2 hydrogen with chlorine at adjacent positions 1 and 2 would produce two distinct isomers. So isomer A, in isomer A, the chlorine groups attached to two carbons are linked by single carbon, which is the longer carbon-carbon distance. And in isomer B, the chlorine groups attached to two carbons linked by double bond would have basically shorter carbon-carbon double bond distance. So these isomers would have different physical and chemical properties. And in the delocalized structure, the modern model, the benzene's pi electrons, they are delocalized, evenly distributed, and it makes all carbon-carbon bonds identical in length and bonding character. And thus only one 1,2-dichlorobenzene structure exists because the chlorine groups, they're attached to carbons with identical environments. So basically the answer is calculus structure would predict two isomers for 1,2-dichlorobenzene, one with chlorine groups on a carbon-carbon double bond and another on a carbon-carbon single bond. And only one, but the experimental observation shows only one 1,2-dichlorobenzene exists, and this agrees with the delocalized structure where all carbon-carbon bonds are identical. So the chlorine groups, they're indistinguishable in position. So here is the answer. Moving on to the next question. State how the enthalpy changes of hydrogenation for cyclohexane and benzene provide evidence for the delocalized structure. So cyclohexane has one carbon-carbon double bond here. And when hydrogenated to cyclohexane, the measured energy, enthalpy change of hydrogenation is minus 118 kilojoule per mole. And for calculus prediction for benzene, if benzene had three isolated carbon-carbon double bonds, as in calculus structure, its hydrogenation would be expected to release 3 times minus 118, which gives us minus 354 kilojoule per mole. But the experimental results for benzene, the actual enthalpy for hydrogenation of benzene is minus 205 kilojoule per mole, which so much less exothermic than calculus prediction, and the difference of plus 149 kilojoule per mole, so minus 205 versus 354. It's called the resonance energy or delocalization energy, which is an extra measure of benzene's extra stability. So lower than expected enthalpy means benzene is more stable than calculus structure predicts, and the stability arises from the pi electron delocalization resonance, which lowers the energy of the molecules. So the answer is basically the experimental enthalpy of benzene minus 205 kilojoule per mole is less exothermic than expected for calculus structure, which is minus 354 kilojoule per mole, proving benzene is stabilized by delocalization. So here is the answer. Moving on to the next question. Here, describe the structure of benzene in terms of atomic orbitals involved, the bonds formed, and the delocalized electrons. So we have to explain in terms of the atomic orbitals involved. Yeah, atomic orbitals involved. So basically the types of orbitals and their roles, the bonds formed, basically sigma or pi bonds, and the delocalized electron, and how they contribute to benzene stability. So the atomic orbitals involved. So we know that each carbon atom in benzene is sp2 hybridized. So sp2 orbitals, they form sigma bonds with two adjacent carbon and one hydrogen bonds, and the remaining pi orbital, the unhybridized, on each carbon contains one electrons, and the bonds formed is the sigma bonds, which is formed by head-on overlap of sp2 orbitals, the carbon-carbon and the carbon-hydrogen, and give benzene its planar hexagonal structure, making all bond angles 120 degrees. In the pi bonds, it's formed by a sideways overlap of 6 pi orbitals or 6p orbitals, 1 per carbon, and these pi electrons, they're delocalized, which is basically spread evenly over all 6 carbons. And the delocalized electrons, the 6p orbitals, they merge into continuous pi system above and below the ring, and this creates a ring of electron density not fixed to specific bonds, and the resonance stabilization, so extra stability compared to isolated double bonds. So the answer is that each carbon uses sp2 hybrid orbitals to form sigma bonds and has 1 electron in the p orbital. The benzene has sigma bonds, carbon-carbon and carbon-hydrogen, and all delocalized pi bonds from overlapping p orbitals. And the 6p orbital electrons overlap to form continuous pi system, stabilizing the molecule. And here is the answer.